In this video, we are going to look at section 1.8 from your book on logarithmic functions. This should be a review for you, so hopefully you will remember some of the things you've done with this in the past. So a logarithmic function is really an inverse of an exponential function. That's why these two are written right next to each other. That's what it says here. For any exponential function, f of x equals a to the x, its inverse is called a logarithmic function, base a. So the inverse of f of x equals a to the x is really f inverse of x equals log base a of x. That will come in useful when we go to solving logarithmic and exponential functions. Before that, we want to be able to translate our understanding of exponential functions and how that works with logarithmic functions. And this is what we use to translate. So if you know that a number to a power equals some value, the way you rewrite it as a log is this exponent is the answer of the log function. So whatever the exponent was equals the log base a, which is written as a subscript, of x, which used to be the answer. Let me show you what I mean. Up here, since 3 squared equals 9, we would say the log base 3, so that's a subscript, of 9 equals 2. So the answer is the exponent. Since 5 squared equals 25, the log base 5, whatever the base was on your exponential, becomes the base of the log. So log base 5 of 25 would equal 2. If 2 cubed is 8, log base 2 of 8 is 3, the exponent. If 3 to the negative half, or to the negative 2 power is 1/9, then the log base 3 of 1/9 equals -2. If 2 to the 0 power equals 1, then the log base 2 of 1 is 0, the exponent. If 2 to the 1/2 equals, should be there, the square root of 2. This is written wrong. So the log then base 2 of the square root of 2 would equal 1/2. It always equals the exponent. If 4 cubed equals 64, then the log base 4 of 64 would be 3. The logarithm equals the exponent. So here, on these two where we have log base 10, if it says the log base 10 in example 1 of 10,000 would be what? We're going to do this without a calculator. What this is asking, of course, is 10 to the what power equals 10,000. So 10 times 10 is 100. You can kind of do it on your fingers and figure out that it's 10 to the 4th power that equals 10,000. So the log base 10 of 10,000 is 4. Here, it's asking 10 to the what power equals 0.01, because it says the log base 10 of 0.01 equals. So 10 to the what power is 0.01. Well, 0.01 is 1/100th. That's in the 100th place, so 1/100th, which is the same as 1 over 10 squared. 10 squared, oops, which means it's 10 to the -2. So the log base 10 of 0.01 is -2. Here, the log base 9 of 3 is, so it's asking 9 to the what power equals 3. Well, it just so happens that the square root of 9 is 3. And you remember from your previous section that the square root means 9 to the 1/2 power would equal 3. So here, when it says log base 9 of 3, the answer is 1/2. Log base 6 of 1 is asking 6 to the what power equals 1. Well, the only thing that gives us an answer of 1 as an exponent is if the exponent is 0. Here it's asking log base 8 of 8. This is a unique situation, but it's an important. It's asking 8, what power of 8 will give us an answer of 8? And that, of course, is to the 1st. So anytime you have a logarithm where its base is the same as its argument, as in this case, log base 8 of 8, your answer is going to be 1. So similarly, if I had log base 6 of 6, that would be 1. All right, so this little box here says logarithmic function base A. We define the y equals log base A of x as the number y such that x equals a to the y. That's what we had written above, where x is greater than 0 and a is positive constant other than 1. So the point of this is to show the pictures that we have here kind of indicate how logarithms and exponential functions are inverses of one another. Because, as you might recall, inverse functions are reflections over the line y equals x. So here we have y equals 2 to the x, and its inverse is going to be the log base 2 of x. They are reflections over the line y equals x. Similarly here, we have y equals e to the x, and natural log is the same as log base e of x. And you can see that those two would be inverses because they are reflections over the line y equals x. And here, this is f of x is, sorry, I'm not drawing that very well, but this is 1/2 to the x power. This would be the log base 1/2. So they are reflections over the line y equals x. So they're inverse functions. All right. Let's convert each of these in example 2 to logarithmic equations. Here, if I've written 16 equals 2 to the x, we would write that as the log base 2 of 16 equals x. This base on my exponential function becomes the base of my logarithmic function and is written as a subscript. So we have log subscript 2 of 16 equals x, because remember, logarithms always equal the exponent. All right, try these next two, and then we'll look at them together. On B, we had 10 to the negative 3 power equal 0.001. So that would be written as the log base 10 of 0.001 equals the negative 3. Now, when we have log base 10, we don't actually have to write the 10. This is called the common log. So log base 10, you can write without the subscript. If you see a log without a subscript, it's understood to be base 10. Over here, we had on part C, e to the t equals 70. So that would be log base e of 70 would equal the exponent of t. But similar to before, if we have log base e, that is ln, or the natural log. So that's how those are identified on your calculators too. You see ln. That means the natural log base e. Now we're going to do a similar conversion in example 3, except we're converting it to an exponential equation. In part A, we have log base 2 of 32 equals 5. We would convert that using the base 2. This is our exponent to the 5th equals 32, and you can check that and convert it and make sure it's correct. Go ahead and try B and C and put them together. So in B, we had the log base A of Q equals 8. That means our base A is being taken to the 8th power, and it would equal Q. In part C, we had log base T of M equals X. So that means T to the X power would equal M. Let's find logarithms on the calculator. So finding logarithms on the calculator. Most calculators come equipped to handle log base 10, which they just write as log, or log base e, which they just write as ln, respectively. So find each of these values on your calculator, and let's check them. We want to round to 4 decimal places here. When you plug these into your calculators, the log of 645,778 came out to be about 5.8101, because you rounded to 4 decimal places. In B, the log of 0.00000234 wound up being about a negative 0.56308. And in C, the log of negative 3, you can never have a negative argument. This part here of the logarithm is called the argument. It can't be done. It is undefined. Why? Because there is no power of 10 in here that'll give you a negative value. If you take 10 times 10, or in any different way, you're never going to get a negative answer. So this number in here can't be negative. Let's go ahead and do the same thing with natural log on number 5. On your calculator, find the natural log of 645,778, the natural log of 0.0000456, the natural log of -5, you know what that's going to be, the natural log of e, and the natural log of 1. Let's see what you get. So for A, we got that the natural log of 645,778 to be about 13.3782, rounded to 4 decimal places. In B, the natural log of 0.0000456 to be about -0.9956. And in C, the natural log of -5 can't be done because it's undefined. In D, the natural log of E is really the log base E of E, and we know E to the first equals E, so that has to equal 1. In part E here, the natural log of 1, and that's got to be 0 because E0 equals 1. All right, let's hit the change of base formula. So if this problem, the change of base formula is used if you can't do it in your head, right? If I would have had the log base 5 of 25, I know that's 2 because 5 squared is 25. Here I have the log base 5 of 8. Well, 8 is not a power of 2, so how do we do this? We can do this using the change of base theorem because some of your calculators won't do this on their own. So what we do is if we have the log of base b of m, you can take the log of m and divide it by the log of b. And you can do this using either common log or natural log. Let me show you what I mean. On 6, we could say to find the log base 5 of 8, we could take the common log of 8 and divide it by common log of 5. Let's do that and see what we get. On your calculators, if you take the common log of 8 and divide it by the common log of 5, you get 1.292 approximately. And that is what the log base 5 of 8 is. We just use this change of base there. Now, it also works if we would have used the natural log of the 8 divided by the natural log of 5, and it gives us the same answer. So it's a totally cool way to be able to find a value if your calculator won't change the base on its own. Okay, so example 7 did the same thing as I just did in example 6. So how can this help us if we're graphing? Well, again, if your calculator will not graph the log base 5 of x, what you'd want to do is in your calculator's graphing mode, you'd want to graph log of x divided by log of 5, and that will give you the graph of the log base 5 of x. Let's do that and graph it. The graph should look something like this. This is what most of the logarithmic graphs look like, but this will be unique because it is the graph of the log base 5 of x. So it's going to be a little bit flatter along here and a little bit steeper back over here than like log base 2. Now, if we wanted to graph the natural log of x, your calculator will do that. So you'll just type in the natural log of x, and you'll get something that looks like this. It's a little less flat over here. This one's flatter, and it's going to be a little less steep over here. That would be the graph of y equals the natural log of x. In our next video, we're going to look at properties of logarithms, which will help us as we go to solve exponential and logarithmic equations. Thanks for watching.